In this video, we are going to get a quick overview of how to create and run a SWAT model using QSWAT. SWAT, which stands for Soil and Water Assessment Tool, is a continuous time semi-distributed process-based watershed scale model developed and maintained by the Texas A&M Agri-Life Research and USDA's ARS lab in Temple, Texas. It can do hydrology, water quality, plant growth, and agricultural management. So SWAT is a comprehensive model. QSWAT is a QGIS plugin to create, run, and visualize SWAT model results. And ArcSWAT is an ArcGIS tool to create and run a SWAT model. SWAT is an open source software, which means that you can get access to its source code, but QSWAT or ArcSWAT, they are available in public domain for free, but you do not have access to the source code for those plugins. This is how the interface looks like in QGIS. So this is QSWAT interface, and this is what we'll be focusing on in this module. This is the link from where you can get the latest and earlier versions of QSWAT. The version that we are going to use in this module is shown here, QSWAT 3 1.1.1. As mentioned earlier, SWAT is a comprehensive model. It can do hydrology, water quality, agricultural management, and much more. In this module, we'll be focusing on just the hydrology part of SWAT. For hydrology, SWAT can do surface water, it can do subsurface, it can do lateral subsurface flow, it can do redistribution, it can do percolation, it will do surface runoff and pond and channel processes, and also evapotranspiration. This is the main water balance equation in SWAT. So what you see here is soil water content at any time step, and we will be doing a daily time step model. So soil water content on any given day is equal to the soil water content on the previous day plus the summation of all these fluxes. So what we have here is precipitation on that day, surface runoff, evapotranspiration, subsurface flow, and percolation. And then for the surface runoff, it uses the curve number equations. This is the main curve number equation, but the difference between the curve number equation that is used here and in any other model, especially HMS, this S, which is the maximum soil retention, is calculated by using the soil water profile. And this is the equation that SWAT uses to create the maximum soil retention parameter, and this is used in the curve number equation, and then this is used here to calculate the soil water balance. So this is a very quick overview of the hydrology used in SWAT. You can look at this document to get more information on how all these are calculated. These are the steps involved in creating a SWAT model using QSWAT. So there are 6 steps, and what we are going to do is we are going to look at each step briefly, and you will follow these steps in more detail in subsequent videos. So the first step is to create an empty project. So what you do is you open QGIS, you launch the plugin, and then you create a new project. When you create a new project, what QSWAT will do is it will create all the files and databases that you will need to run the SWAT model. So these are these folders. Within each folder, we will have more files as we perform next steps. And this is the project database. This is the reference database where it will have default parameter values, and it also uses a soil database, which we will talk about when we do the module. So essentially, QSWAT is an interface to create the input files that we need to run the SWAT model. After we set up a project, the next step is to delineate watershed and sub-basins. This process is similar to what we have done earlier using ArcGIS tools, and HMS. So what you need here is a digital elevation model, which you see here in the background. Then you specify the threshold that you want to use to delineate the streams, and it will delineate the stream network. After we specify the outlet point, it will delineate the watershed boundary and the sub-basins based on the stream network. This is the basic step to create this sub-basins and stream network. But if you want to burn the streams, you have option to do that. If you have existing data that you want to use, there are options to do that. But in this module, we will just use a DEM and an outlet point and a threshold to delineate our stream network and sub-basins. In HMS, all the calculations are done at the sub-basin level. In SWAT, all the calculations are done at the HRU level. So HRU stands for Hydrologic Response Unit, and it is a unique combination of land use, soil, and topographic slope. So in order to create hydrologic response unit, you need land use, you need soil, you need DEM to extract the topographic slope, and since these HRUs are calculated for each sub-basin, you will also need the sub-basin file. So as I mentioned earlier, all the calculations are performed for each HRU within the sub-basin, and the calculations or the results are then lumped to provide output at the sub-basin level. Since this is an important concept in discretization of a watershed in SWAT, let's look at how HRUs are created. So what you have here is a hypothetical land use data set. So we have three types of land use: agriculture, forest, and urban, and the total area of this sub-basin is 1000. So you can think of this as 1000 kilometers square or 1000 square miles, but let's just call it as 1000 units. And then we have soil. So there are two types of soil that are present in this sub-basin. X, it occupies an area of 880 units, and Y occupies an area of 120 units. Now to create HRU, you will also need to have topographic slope, but just to keep it simple, we will just look at land use and soil. So after we overlap the land use and soil, you end up with these 6 combinations. So what we have here are 6 HRUs. So there are multiple ways of using HRUs in SWAT. You can use a single HRU based on dominant land use. So the dominant land use is agriculture here. Or you can use a single HRU based on a dominant soil. So the dominant soil here is X. Or you can use a single HRU based on the dominant combination. So the dominant combination in this case is AGX. What we have done here is we have combined agriculture and X to create AGX, urban and X to create URX, urban and Y to create URY, and forest and Y to create FOY. So if we do not use single HRU, we can use multiple HRUs, and in this case we end up with 6 unique combinations of land use and soil. Since this is a hypothetical sub-basin, we have 6 combinations that we can use as HRUs, but in a real data set we end up with thousands of combinations. So in that case, what we try to do is we try to reduce those combinations by applying area thresholds related to land use and soil. So let's look at how that thresholding works. So what we are going to do first is we are going to apply a 20% land use threshold. Since our total area is 1000, what you see in this column is the percentage occupied by each land within the sub-basin. So agricultural occupies 50%, forest occupies 32%, urban occupies 18%. This is our land use map, and this is our HRU map that we got in the previous slide. So we have 6 unique combinations here. Now if you look at this column, you can see 50% is higher than 20%, so this land use will stay. 32% for forest. So this is again higher than 20%. Forest will stay, but you can see urban is only 18%, which is below our threshold. So urban will go away. Since this land use will go away, what we then do is we proportionately assign this area to agricultural and forest by using these expressions here. So again, this is just a proportional distribution of 180 to agriculture and forest, and now they get 610 units for agriculture and 390 for forest. Since urban went away, URX and URY will go away, and we end up with four combinations. So AGX, FOX, AGY, FOY. Since agriculture got 610 and it overlaps with Y, so Y will also get some area, and how this 49 was calculated is given here. It's simple calculation involving proportion based on that area within that land use. So after we apply the land use threshold, we end up with four HRUs, and their areas are given here, and they again add up to 1000 units. After that, let's apply a 10% soil threshold. So we have these two land uses now, and these are our four unique combinations after applying land use threshold. Now we calculate the percentage of each HRU corresponding to soil and land. So what we have here is these are the areas of each HRU. Now we see how much is that corresponding to each land use. So the percentage of area that you see here, 92%, this is calculated as 561 divided by 610. This will give you 92. This is 341 divided by 390 will give you 87.4. Now 49 divided by 610 will give you 8%, and 49 divided by 390 will give you 12.5%. So you can see from this column that AGY does not meet our 10% threshold, so it will go away, and eventually we end up with three HRUs, and their areas are again shown here, and they add up to 1000. After we remove a HRU that does not satisfy our threshold, we have to proportionately reassign that area to the remaining HRUs, and this is what we get at the end. So this is how HRU concept works in SWAT. The idea here is again to reduce the number of combinations so that the calculations can be performed faster. This is the interface that we have in QSWAT to create HRUs. After we delineate watershed, this will become active. So after you click here, this is the interface that we have. We have to specify the land use data set, we have to specify the soil, we have to specify the thresholds, and then there is also option to reclassify soil, land use and topography, and again reclassification is to reduce the number of categories we have in each data set. After you specify the threshold and create HRUs, what SWAT will create is an HRU report. So these HRUs are not spatially connected polygons. So again, these are just unique combinations of soil, land use and slope. And you can look at the report, and this is how HRU report for a specific sub-basin looks. These are the land use that satisfy the threshold, these are the soil that satisfy the threshold, and these are the slopes that satisfy the threshold. And you can see the combinations that are created by using these land use, soil and slope. After HRUs, our last step is to create input files before we run simulation. So again, there are two steps involved here. So the first step is to connect to all the databases that SWAT needs. It will need the project database to get access to all the sub-basins and reaches. It will need access to the parameter database, and it will also need access to the soil database. And then this is the place where the SWAT executable file is stored. After we connect to these databases, it will have access to the parameters and soil information. It will also need access to weather information. So there are two ways by which we can provide weather or climate data. One way is to just use the internal weather generator within SWAT, and which is what we will use in this module. But you can also use gauged observations related to temperature and precipitation, and how to do that is explained in the handout that will be provided with the module. Once you connect to the databases and select the weather data, then we are ready to create all the input files. So you can see there is a long list, and many of these files are created by using the default parameter values that the SWAT will get from these databases. So you click OK and create all these input files. SWAT will create hundreds of input files depending on how many sub-basins and HRUs you will have in your project, and you can access those files by going to the scenarios folder. Within scenarios folder you will see a folder called default, and within that default folder you will see a folder called text in out. And the input files are created at three levels: at the watershed level, at the sub-basin level, at the HRU level. Since it creates hundreds of files, then the question is, how do we know which one is at the watershed level, which one is at the sub-basin level, and which one is at the HRU level? All the files at the watershed level will have some name and some extension. All the files at the sub-basin level will have some numbers corresponding to each sub-basin, and then there are 4 zeros after that and an extension. So this is a 9-digit number, the first 5 digits corresponding to the sub-basin number and the last 4 digits corresponding to the HRU within that sub-basin. So when the last 4 digits are 0, then it's a sub-basin file. If all 9 digits are populated, so you have sub-basin, you have HRU, then it's a HRU level input file. These are some of the example files that we get at the watershed level: file.cio, configuration file which is named fig.fig, basins information basins.bsn, and these are the extension at the sub-basin level file. These are the extension at the HRU level file. These are just some examples, so it will have more files than this. This is how the file.cio file looks like. So this is the watershed scale file, and the information that is contained here is when the simulation starts, when the simulation stops, whether precipitation data is observed data or simulated data. Similarly, whether the temperature data is simulated or measured. So 2 means it is simulated, and if it was observed data, then how many number of gauges and so on. So this is how file.cio looks. This is another watershed level file. This contains information about sub-basins and what processes will be used to calculate the water balance, runoff, nutrient recycling, and many more processes that we don't see here. This is a sub-basin level file, so you can see the last 4 digits are 0, and this file contains information about the processes that are used in the sub-basin and the parameters that are used to simulate processes in sub-basin. This is a HRU level file, so this file contains information about the parameters that will be used in simulating subsurface and groundwater flow. After we create the input files, we are finally ready to run the simulation. So this is the interface for running the simulation. We have to specify the start date, end date, and these dates should match with the information that we have provided for the climate or weather data. We have to pick what version of SWAT we have. We have to pick whether we want daily simulation, monthly simulation. We also want to specify the number of years that will be used for warm up, And once you do that, you set up the SWAT run and then you run SWAT. As I mentioned earlier, this is just an interface to execute SWAT model, and when the SWAT model is executed, this is what you see here. So the model is being executed for each year, and if you perform it for 10 years, you will see simulating for year 1, year 2, year 3, and up to year 10. After you run the simulation successfully, you can check the water balance, and this is again available with the QGIS interface. You can run the check and see how much water is getting distributed into evapotranspiration, subsurface, surface runoff, and so on. So you can do a quick check and make sure that the water balance looks right. If not, you can change the parameters and other inputs and rerun. QSWAT will also have tools for visualization. After you run the simulation successfully, you will have access to this visualize button. It has tools to do spatio-temporal visualization, which means what you see here is the runoff changing within each reach, and you can animate this, or you can also look at the hydrograph at the sub-basin level or at the watershed level. So what you see here is the hydrograph for the entire simulation period, and what you see here is surface runoff within each reach. Similar to input files, output files will also be stored in the default folder, and if you give a name to your simulation, it will be available in that folder, and the name here implies that there is a certain name associated with that simulation. These are some of the files where you can find all the outputs. So there is input.std. This is just the summary of all the input. And then there is output associated with reaches, hydrologic response unit, sub-basin, watershed scale, reservoir output, and sediment loading. So depending on whether you want to look at the reach scale output, HRU scale, or sub-basin scale, you can open any of these files. These are all text files, and if you click or open some of these files, this is how they will look. This is a reach scale output, so you will see RCH here. So this is the reach, this is the day, flow coming into that reach, flow coming out of that reach, evapotranspiration loss, and sediment, and so on. So for hydrology, we are mostly interested in the watershed outlets, so you will have to find out the reach that is exiting the watershed, and this column will give you the hydrograph for the outlet. This is at the sub-basin, so we have sub-basin number, day, and again precipitation within that sub-basin, snow melt, PET, ET, surface runoff, and so on. This is it. So what we got here is a quick overview, and we will look at the detailed steps involved in doing all this in the subsequent videos. Thank you.